Today I want to talk about the Big Bang model's energy conservation problem. And you can see the problem up front because originally you had nothing and then you had something. So you have something coming from nothing, which can't happen. So it's a violation of conservation of energy because in the original model of the Big Bang there was no energy. They imagined a space that wasn't space. It wasn't real space. It didn't have energy. It didn't have dimensions. Didn't have time. And then all of a sudden, boom, there's a bang and there's all this energy. And then matter and then this energy that causes expansion. So all this energy came from nothing in the original Big Bang model. Now, in an attempt to fix this, in inflation theory, they say, that the general relativity allows for negative gravity, that gravity works in the opposite direction and causes space to expand. And then once you have space, you have gravitational potential energy, the potential energy that's pushing the universe back together if the gravitational potential energy were real like that. And then you have this potential energy that gives you positive energy that gives everything in space. So that's kind of the story. But it falls apart because you need energy to have this negative gravity that pushes everything apart. You need lots of energy. So they steal this energy from this fictitious positive energy, positive gravity idea, or negative gravity idea that works in the wrong direction. And then you get negative gravitational potential energy that wants to push it back together again. And that energy is where you supposedly get all your mass energy, which if it took all that energy would stop the push, but it doesn't really stop the push. So the gravitational potential energy is still there. So the whole thing doesn't make sense. They steal energy at the beginning from out of nowhere, violating the laws of conservation of energy in order to have this negative gravity to cause the expansion. And then they steal gravitational potential energy that doesn't go away in order to make matter and all the other forms of energy in the visible universe. So, and they don't really have enough energy to account for the quantum field energy. They ignore that, and they ignore the dark energy, because this energy causing expansion can account for the dark energy. So they still have a huge conservation of energy problem. They don't account for the expansion, they don't account for the dark energy, and they don't account for the quantum field energy. And in reality, all real space has quantum field in it, and it contains quantum fluctuations. Quantum fluctuations have wavelengths and frequencies, which means the quantum field has dimensions and time. It also has permittivity and permeability, the electric and magnetic constants. And electric and magnetic constants equal 1 over c squared when they're multiplied together, giving us the speed of light squared. So permittivity, permeability, and the speed of light emerge from the quantum field, as does every other physical constant, including g, which is basic Newtonian type gravity. And if we look into the origin of this Newtonian gravity, the quantum field induces a pressure force due to electromagnetic interactions in the quantum fluctuations that pushes on all bodies of matter. This is like the Casimir force, where two plates are pushed together. So we have, in all cases, two objects can be pushed together. In many cases with electrically charged objects, we have differentials in pressure due to electric charge polarity, whether it's attractive or repulsive, whether you're like charges or opposite charges. where light charges are repelled and opposite charges attract because they're pushed together. The same thing happens with gravity. Objects get pushed together. And this energy comes from the quantum field. It's the quantum field that pushes objects together. And that's another problem with the Big Bang model and their gravitational models together. They don't explain where the accelerating force is. Under general relativity, if you had two bodies in space that were static, they would claim that there's a curvature of the field, which actually would be a straight line, but they don't explain how bodies would actually be accelerated. There's no physical explanation for how two static bodies would be accelerated along that straight line. They just say there would be a straight line between them. And so that's where general relativity fails. They say it's not a force, but there's an acceleration, so there has to be a force, and there has to be a cause for the acceleration. Now we're saved in terms of where does all the stable matter come from, the electrons, protons, and which combine to become neutrons that make up all the stars and galaxies and all the physical stuff of the universe. And that's pretty easy to understand, is if we look at protons and electrons and we look at their structure, we know that protons scatter objects at their charge radius. So they have some sort of structure, spherical structure, that is around a proton. And this structure is composed of quantum fluctuations in current theory. Well, a shell structure of quantum fluctuations at the charge radius displaces quantum field energy that would have been there that's equal to the proton's mass. So the mass energy of the proton is equal to the quantum field energy it displaces. And we see the same thing with electron if we consider the electron has a radius equal to half the Compton wavelength. And you may say, well, the electron doesn't have structure. But if you look at the magnetic moment of an electron is equal to a G factor, which is approximately 2, times the electric charge, speed of light, and a radius equal to half the Compton wavelength, divided by 4 pi. So even though they normally put it in terms of mass, if you put the magnetic moment in terms of the Compton wavelength, you see that by using mass, they're disguising the fact that they're using the Compton wavelength as the size of the electron when they do the magnetic moment calculation. So in reality, the physics of the electron are there's some type of spherical shell at the Compton wavelength diameter that gives the electron its mass and its magnetic moment and its spin. And we have neutrons that are the same size as protons, so they're displacing quantum field energy too. So once we have quantum field energy, we can add matter without changing the amount of energy in the quantum field. So there's no net change in energy when you have stable matter present versus there being no matter present, which is also very different from the way people look at general relativity. They say that stable matter increases the energy in space. Well, it doesn't. It doesn't change the energy in space. There's really no energy gradient in space. So anyway, we have a case where matter can be produced, and matter can be produced continually. It doesn't have to be produced in a one-time event. And that points to a big problem with cosmology. We don't know how the electrons and protons are produced. We know that they are produced, or we're fairly confident they haven't been here for infinity. There should be some sort of production mechanism, and we should be able to figure it out. But until we do, we're just guessing at the cosmology of the universe. We need to know how electrons and protons are made without any matter before we'll really understand the cosmology of the universe. And that's at the heart of the problem with the Big Bang model. It makes all kinds of assumptions that have no basis in reality because we can't answer the basic question yet as to how electrons and protons are produced without any matter. And someday we'll do that. But we can tell that all the energy in the universe originates with the quantum field. And we don't really have a conservation of energy problem. The conservation of energy problem is due to a bad theory called the Big Bang theory. And if we do away with that theory and start with quantum field originating in all of space, and then develop a cosmology around that, and figuring out where the electrons and protons come from without any matter, then we can develop a reasonable cosmology. Well, I hope you enjoyed the video and understand a bit more about the conservation of energy problems with the Big Bang theory. And if you hear people talking about the Big Bang theory, you should talk about its many problems. And you can watch my other videos talking about the black hole problem and various other problems with the Big Bang. And so please like, share, or subscribe. And if you want to learn more about quantum field theory, I have some books that are for sale. And if you buy one of my books, that helps support me. I'm an independent researcher, and your support is dearly appreciated. And I also have a Patreon account, linked below. And I've linked some papers that discuss various aspects of what I've talked about, so that you can look those up if you're interested, and other videos as well on the Big Bang model and other related quantum field theory videos related to other topics in physics. So thanks for watching.